Hello dear student, today we will see theorem on primal and dual problem. So we will see a very most important theorem, that is primal of a primal variable is a dual problem. So let us see the uh, a statement of the theorem. A statement is given as dual of the dual is a primal problems, or we can say that in another word, dual of the given primal problem is a primal problem. That means if you have given a primal problem, then we can say that if you take the dual of that problem and that dual of the problem, so you will get the final result is a primal problem. So hence we can say that dual of the dual is a primal problem, or dual of the given primal problem is a primal problem. So meaning of both statement uh, are same. Okay, so let us we see the proof of this theorem. So let us suppose that consider the primal problem in a standard form. So which is given as maximum z equal to c1 x1 plus c2 x2 plus and so on plus cn xn, subject to constant a11 x1 plus a12 x2 plus and so on a1n xn less than equal to b1. Second constant a21 x1 plus a22 x2 plus and so on plus a2n xn less than equal to b2. So in this way we can write mth term, that is given as am1 x1 plus am2 x2 plus and so on plus amn xn less than equal to bm. So okay, so this is the constant, this is the objective function, and where x1 x2 xn greater than equal to 0, this is the non-negativity restriction, that is called as the primal variables, so which is always greater than equal to 0. So let us consider whole equation number 1. Okay, so this is the primal standard form. Now we will find out the dual of this primal standard form. So there are m number of constants, so therefore we required m number of dual variables. Okay, so let us suppose that let w1 w2 wm be the dual variable corresponding to the given primal problem. Then the dual of the above primal problem can be written as, here is the maximum, so we can write as minimum z star. Okay, so this b1 b2 bm will becomes uh, objective function of a dual variable, that is b1 w1 plus b2 w2 plus bm wm according to our definition. Okay, so subject to constant, so this column will becomes row. Okay, that is a11 w1 plus a21 w2 plus and so on plus am1 wm greater than equal to c1, because conversation is minimization, so all the sign should be less than equal to c less than equal to. Okay, second constant, that is second column will becomes row, that is a12 w1 plus a22 w2 plus and so on plus am2 wm greater than equal to c2. So last term, that is n term, can be written as, this is last term, that is a1n w1 plus a2n w2 plus and so on plus amn wm greater than equal to cn, where w1 w2 wm greater than equal to 0. So these are the dual variables. So equation number 2, whole equation number 2 is called as the dual of the given equation number 1. Okay, so this is called as the dual problem of a given primal problem. Now multiply -1 to equation number 2 throughout. Okay, we will multiply equation number 2 by -1 whole equation. So we get minus minimum z star, we know that is maximum z. We can write here maximum z equal to minus multiply, so minus b1 w1 minus b2 w2 and so on minus bm wm. So multiply -1 to each term of equation number 1. So this can be written as minus a11 w1 minus a21 w2 so and minus am1 wm, and this sign will becomes less than equal to minus c1. Second constant we can Similarly write down, so here sign less than equal to C2, and similarly we can write down the last term. Simply here we have to multiply equation number 2 by only minus 1. Okay, so this is minus sign, this is minus sign. Okay, so here W1, W2, W3 and Wm greater than equal to 0. So let us we consider equation number 3. Okay, so let us we consider equation number 3. Okay, now let us we consider equation number 3 is the primal problem. Now let us suppose that this equation number 3, we will consider this equation number 3 is a primal problem. Then the its dual is given by. Okay, now we consider equation number 3 is a primal problem. Then the dual of this problem can be written as, here is maximum z, so we can write here minimum z star equal to, so here is sign equal to, so C1 minus C1 C2 C becomes row objective function, that is minus C1 V1. So here V1 V2 Vn are the dual variables, minus C1 V1 minus C2 V2 and so on minus Cn Vn. Okay, so minus A11 V1 minus A12 V2 minus A1n Vn greater than or equal to minus another variable, that is B1. Let us we take B1. Okay, so this column will becomes row. Again this column will become second row and this column will become third row. Okay, so in this way we can write this equation, this first constraint, then second constraint minus A21 V1 minus A22 V2 and so on minus A2n Vn greater than or equal to minus B2 and so on. Last term we can write as minus AM1 minus AM1 V1 minus AM2 V2 and so on minus AMN Vn greater than or equal to minus B. Bm. So here is a m term. Okay, m. So here V1, V2, Vn are the dual variables. Okay, so now equation number, so this is equation number 4. Let us consider equation number 4. Now equation number 4 multiply by minus 1. Now this equation number 4, for this equation number 4 we multiply minus 1 to whole term. Each and every term we will multiply by minus 1. Then objective function will becomes minus minimum z star. So this can be written as maximum z by using our notation minimum z star equal to minus maximum z star, or we can say that maximum z star equal to minus minimum z star. So this can be written as maximum z equal to minus 1 multiply to this term, so this will become whole positive term C1 V1 plus C2 V2 and so on Cn Vm subject to constraint, the whole term will become positive A11 V1 plus A12 V2 and so on. So this sign will becomes less than equal to B1. Okay, less than equal to B1. So second term will becomes positive and sign will becomes less than equal to B2, and in this way last term we can write in this way AM1 V1 plus AM2 V2 plus and so on plus AMN Vn less than equal to Bm. So this is equation number 5. Okay, so this is the equation number 5. Now if you compare equation number 1 and equation number 5, equation number 1, where is equation number 1? This is equation number 1. If you compare equation number 1 and equation number 5, then you will get both equations are identical to each other. Okay, then if you observe equation number 1 and equation number 5, we can say that the both equations are identical to each other, and hence we can say that the dual of the dual is a primal problem. Okay, so if you observe equation number 1 and 5, so you will get the similar format of a primal problem. So and hence we can say that the primal of the primal is dual of the primal problem is a primal problem. Hence this is the proof of the theorem. So this is a very most important theorem exam point of view. Now we will see problems on a duality. So these are the different problem as we have discussed in a previous lecture. So that was only conversations of the primal to dual problem. So this problem is, after conversations you have to solve that problem by using simplex method. So in this problem you have to find out the dual problem. First you have to write down the primal problem in standard form, then you have to take the dual of that problem, then after taking dual of that problem you have to solve that dual variables or dual problem by using general simplex method. Okay, so in this way we can solve by using simplex method dual problems. So you will get the solution in a dual problem, in a dual variables. Then after taking or using the rule of duality, then you can convert that dual optimal solution in a primal solution. Okay, so this is the example, or we can say that this is the procedure how to solve the duality problems. Okay, now we will see the first problem, using duality to solve the following LPP. So given problem is minimum z equal to x1 plus x2 subject to constraint 2x1 plus x2 greater than equal to 4, x1 plus 7x2 greater than equal to 7, x1 and x2 greater than equal to 0. So this is the given problem is in minimum, and if you observe, this is a primal standard form, is in primal standard form. The given LPP is in primal standard form because all the sign are greater than equal to, and problem is minimum. So therefore minimum z equal to x1 plus x2 subject to constraint 2x1 plus x2 greater than equal to 4, x1 plus 7x2 greater than equal to 7, x1 and x2 greater than equal to 0. So this is the primal standard form of a given LPP. Now we have to find out the dual of this problem. So there are two constraints. So we want only two dual variables. So let us we take W1 and W2 are the two dual variables. Then the dual is given by, so maximum Z star equal to 4 W1 plus 7 W2 subject to constraint 2 W1 plus W2 less than equal to 1, W1 plus 7 W2 less than equal to 1, W1 W2 greater than equal to 0. Okay, so this is the dual problem of a given primal problem. Now we will solve this problem by using a simplex method. Okay, so now introducing, so here is a less than equal to sign, less than equal to sign. So here we have to introduce only slack variable. So introducing slack variable W3 greater than equal to 0 and W4 greater than equal to 0 into this given constraint. Then the given constraint can be written as 2W1 plus W2 plus W3 equal to 1. So we can write in the equality form. Then second constraint is W1 plus 7W2 plus W4 equal to 1. So here W1, W2, W3 and W4 greater than equal to 0. So let us we consider equation number 1. Okay. So for this new constraint, we will construct the new modified objective function. We will construct the new modified objective function, and that new modified objective function can be written as 4W1 plus 7W2 0W3 plus 0W4. Okay, so here C1 is 4, C2 is 7, coefficient of W2, C3, C4 is coefficient of W3 and W4, that is 0. Okay, now we will find out the initial basic feasible solution. So putting the decision variable W1, W2 equal to 0 in equation number 1, we get W3 equal to 1 and W4 equal to 1. Okay, so in this way we can find out the starting basic feasible solution. Now we will construct the first simplex table as usual by using simplex method. So YB first column, CB third column, here WB because our problem in a dual variable, and dual variable are W1, W2. So therefore we will take here WB instead of XB, Y1, Y2, Y3, Y4 as it is. Okay, then Y3, Y4, so these are the W3, W4, therefore Y3, Y4 associated cos 0, 0, that is C3 C4 0 0. Then WB means RHS side, that is 1 1. Then 2 1 1 0 means coefficient of the W1, W2, W3 and W4. So 2 1 1 and W4 is 0, not present. Second constant 1 7, W3 is not present, so therefore we will take 0 and last is 1. Okay, so here we can put this element from equation number 1, that is the coefficient of W1 W2. Then find out maximum Z star equal to CB WB. So this is the formula. So CB means 0 into 1 plus 0 into 1, that is 0. So Cj, Zj, Zj minus Cj. Cj means C1, C2, C3, C4. We have found out from objective function 4, 7, 0, 0. Then Zj. Zj means Cb into Yj. So here 0 into 2, 0 plus 0 into 1, that is 0. So Zj here 0, 0, 0, 0. Okay, Cb here 0. So therefore Cb into y1, Cb into y2, Cb into y3 and Cb into y4 will become 0. That means Z1, Z2, Z3, Z4 will become 0. Now Zj minus Cj, that is minus 4, minus 7, 0, 0. Okay. Now here Zj minus Cj less than 0. That means there are some negative value of Zj minus Cj. So therefore this table will not give the optimum solution. Okay. So for that we have to construct the new modified table. So for that we have to find out income vector, outgoing vector and key element. So how will you find out the income vector? So select most negative value in Zj minus Cj. So most negative value is 7. So corresponding vector y2. Y2 will use the incoming vector, will enter the basis. So here y2 is the incoming vector. Then find out minimum ratio. So minimum ratio is calculated as WB divided by incoming vector, that is y2. So this can be written as WB1 divided by 1, that is 1. Then 1 divided by 7, that is 1 by 7. Okay. So if you observe from this both ratio, so 1 by 7 is a minimum ratio. The corresponding vector y4 will use the table, or y4 is the outgoing vector. So here y4 is the outgoing vector. Now key element is the intersection of incoming vector, that is y2 and y4. So here is the intersection of the two vectors, that is element is a 7. So therefore 7 is the key element. Now we will construct the next simplex table. So YB, CB, WB, Y1, Y2, Y3, Y4 as it is. Okay. So what will be the change here? Y3 as it is, only change will be Y4. So replace Y4 by Y2, because Y2 is income vector. Y2 will take the position of Y4 and Y4 will outside of the bracket or table. Y2, Y3, Y2. So C3 is 0 and C2 is 7. So WB. Now we will find out these elements. So divide this key element to the key row. So this can be written as 1 by 7, 1 by 7, 1. So here we will take 0, then 0, 1 by 7. So in this way we can find out the key row element. Then above element we can find out by calculating each element. Okay, so you can calculate in previously. Okay, we have calculated in general simplex method, two phase method, BGM method, as well as simple methods, general simplex method. Okay, so you can calculate all the remaining elements. Then maximum Z star CBWB, so we can calculate 0 into 6 by 7, 7 into 1 by 7, that is 1. So Cj means C1, C2, C3, C4, that is 4, 7, 0, 0. Zj means Cb into Yj, Cb into Y1, that is 1, Cb into Y2, that is 7, Cb into Y3, that is 0, and Cb into Y4, that is 1. So in this way we can find out Z1 1, 7, 0, 1. So Zj minus Cj means 1 minus 4, that is minus 3, 0, 0, 0, 0. Okay. So here again Zj minus Cj is negative value. So therefore this table will not give the optimal solution. Therefore we have to construct a next simplex table. So for that we have to find out incoming vector. So select most negative value from this table. So corresponding vector y1 is the incoming vector. and find out the outgoing vector by computing minimum ratio. So minimum ratio is WB divided by incoming vector. So WB means 6 by 7 divided by 13 by 7. So this can be written as 6 divided by 13, and this is 1. So if you observe, so first ratio 6 divided by 13 is the minimum ratio. The corresponding vector y2 will use the basis, that is y3 is the outgoing vector, not y2, y3. Y3 is the outgoing vector. Now key element, how will you find out key element? The incoming vector and outgoing vector, intersection of incoming vector and outgoing vector. So that is 13 by 7 is the key element. Okay, so now we will construct the another table, that is next table. Okay, so YB, CB, WB, Y1, Y2, Y3, Y4 as it is. Okay, what will be the change here? So Y3 replaced by Y1, Y1, Y2 is as it is. So C1 is 4, C2 is 7. Okay, then we will find out the first this element, that is dividing 13 by 7 to this key row. So you will get the this element up to this element. Then so here will become 0, here will become 0, that is this 0. Okay, and then another variable, another terms you can find out the by using calculation. Okay, so in this way we can find out the all the elements of this simplex table. Then find out maximum z star, that is CB WB, and which is given as 4 into 6 by 13 plus 7 into 1 upon 13, that is calculating 31 by 13. So Cj means C1, C2, C3, C4, Zj means Cb into Y1, that is 4, then Z2 means Cb into Y2, then Z3 means Cb into Y3, and Z4 means Cb into Y4. So we will get these elements. So Zj minus Cj means 0, 0, 21 by 13, 10 by 13. So here all the elements of Zj minus Cj greater than equal to 0. Okay, positive, and hence we can say that this table will give the optimum solution. Therefore the optimum solution is given by W1 is 4 and W2 is 7, because our problem is in W1 is 16 6 by 13 and W2 is 1 by 13, because our problem is in dual variable. So therefore maximum z star equal to 31 by 13, maximum z star equal to 31 by 13. Okay, but our actual problem is in a primal. Okay, so therefore we have to find out this solution in a primal form. So by using the rule of duality, we can obtain the required solution of the given primal problem as x1 equal to 21 by 13. So this is x1, this is x2, x1 equal to 21 by 13, x2 equal to 10 by 13. Okay, so you have to select from this x1, that is first slack variable means x1, and second slack variable means x2. Okay, so in this way we can find out the primal variable. Primal variable x1 is 21 by 13 and x2 equal to 10 upon 13. Then putting the x1 x2 value in original objective function, that is minimum z equal to x1 plus x2, so you will get 31 by 13. So this is the required solution of a given problem. So this is the primal solution of a given problem. So here you have to note that the solution of any primal problem and dual problem, both the solutions are equal. Objective function are equal, because it gives the minimum value and maximum value equal. Okay, so this is the complete examples on a duality.